ATS EVS 105 students, we're ready to start taking on the third module of this course. And in this module, we're going to be talking about some of the basics of the physics of climate. What determines the climate of an area? And in particular, we're going to be talking about radiation and the movement of heat through the atmosphere and through the climate system and so on. And in order to understand this, we need to have a good handle on the ideas of energy and power and the basic laws that describe how radiation moves and so on. And that's what we're getting today from the reading that you have done in your textbook. In the first printing of the book, that is pages 34 through 42. Now, every textbook that has to talk about ideas like energy and power and so on starts off with this somewhat unhelpful definition of energy, where it says that energy is the ability to do work. I don't know anybody who that ever helped, other than to recognize that that probably means energy and work are kind of the same thing. In fact, it gives physics professors chest pains when they hear meteorologists say such a thing. But to a good approximation, energy and work and heat are all kind of the same thing, and they all have the same units and so on. When we say work, in the context of like climate, work is stuff like moving air around, wind and things like that, lifting volumes of air, causing them to expand and so on. That's all examples of what we call work in the context of like climate science. The units of energy are called joules. Now that might not be a term that you're terribly familiar with. The symbol for the unit of energy is J for Joule, and it's named in honor of James Prescott Joule. We're going to see a bunch of these old dead white guys of science today, just as kind of something we don't do every day. James Prescott Joule, according to Wikipedia, was an English physicist and brewer, which I love it, the fact that they all have these other interests outside of science. And he was one of the people who studied the nature of heat and so on, determined the absolute temperature scales and so on. Good old James Prescott Joule is whom we named the unit of energy after, the joule of energy. Now there are other ways that we can describe the amount of energy that an object has. In fact, one that we're going to be seeing if you stick with ATS EVS courses and make the big transition next semester to take ATS 113, you'll be working with calories as the unit of heat. I don't much care for calories as a unit of heat, but it tends to be what we use in the textbooks for those kind of courses. But a calorie is a unit of heat or energy, and in fact it is related to the idea of like calories in food. A food calorie is strictly speaking a kilocalorie, or 1,000 energy units of these calories. But it is also a unit of energy. It's the energy that your body can extract from the food. So I can think about energy. I'm still not entirely sure what I mean by energy other than it's an ability to make things happen. And we can transfer energy from one object to another by moving it in the form of power. Power is the rate, rather, that energy is moved. I'm here in my basement green screen studio, and I am surrounded by lights that are drawing power. They are drawing energy off the grid at a certain rate. The number of joules per second that they are drawing off the grid is how much power those lights have. So, maybe that's a 45-watt light, and these are some fluorescent lights over here that draw very low. I think they're 9-watt and so on. Notice, though, that I'm saying here, the unit of power is watts. A joule per second, that much energy per second, is a watt. Joules per second written out, or J/S for joules per second. Even better, just to kind of get comfy with the way scientists write things, J and then an S to the -1. To the -1 means, per. So, joules per second. And they are named after good old James Watt. Again, just to talk about an old dead white guy of science, he is, according to Wikipedia, a Scottish inventor, a mechanical engineer, and a chemist who invented a type of steam engine and perfected a different type of steam engine and set in motion the Industrial Revolution both in his native England and worldwide. So we sort of have James Watt to blame for all of our post-Industrial Revolution problems in the climate world. But all of this is not so hard to think about if you're like in the context of a light bulb. Okay, in terms of a light bulb, I can picture how energy is moving down the wires to the light bulb and being at a certain rate, a certain number of joules of this energy per second are passing through the light bulb and creating light. And we are using that energy in this case to produce light. I can think of other senses of energy as in like the energy that's being stored in food, or the energy of like, kinetic energy of something in motion or something. But in the context of climate, an important type of energy we need to understand is internal energy. Now, internal energy is not like as in, the kinetic energy as we move this object up and down, or anything like that. Internal energy is kind of hard to define. Your book tries to say that it is how fast the molecules are moving. I mean, you guys all know that stuff is made of molecules, and even when something is just sitting still, the molecules are wiggling and so on. And in the case of a gas, they're just zipping around all over the place. Okay, I don't like that definition of internal energy because it isn't really how fast the objects are moving, it's strictly speaking their kinetic energy. I know that this turns out to not be a huge factor in this particular lecture, but it does, especially since most of the people will probably continue into ATS 113, and there this becomes a big deal. I want to make sure that we're clear about the idea that internal energy is actually about the kinetic energy that all the little molecules that make something up have. And kinetic energy, if you survive like a high school physics class or something, you know the kinetic energy is related to both the velocity that the objects are moving, v, and their mass, m. In fact, it's 1/2 mv squared, if that happens to be something you vaguely remember having seen before in like a high school physics class or something like that. Well, so all of your little molecules are moving around. Each one has a little bit of mass, and each one's wiggling around. Their kinetic energy is like if you added up all the kinetic energy of all those little molecules that make something up, that's how much internal energy it has. That's very closely related to the idea of temperature. You can imagine in a class that's about climate change and global warming, that's where we're headed with this stuff, is understanding how the temperature is affected. Now, your book again throws out this definition that I'm not sure is that helpful, where it says that temperature is a measure of the internal energy of an object. It might be better to say, though, that it is a measure of the kinetic energy of all the molecules in the object. So all those little molecules that make up the object are all wiggling around, and they all have kinetic energy. You add them all up, and that's kind of what temperature is it's a measure of their kinetic energy. The fact that it's kinetic energy is important because most materials are made up of a bunch of different things mixed together. I'll take air as my example here. Air is a mixture of lots of different gases. All those molecules are mixed together. Some of those molecules are very light. We'll get into that more in other courses and so on, but water vapor molecules are very light. For example, obviously things like hydrogen and helium are very light. In contrast, there's gases that have surprisingly heavy molecules, carbon dioxide, nitrogen, and so on. Some of these molecules are light and some of them are heavy, but if the temperature of this mixture of gases is about the kinetic energy of all those molecules, well, since some of the molecules are light, to have the same amount of kinetic energy as the heavy ones do, the light ones have to be moving pretty fast. When you mix the gases together, no matter what those gases are, they all have the same temperature. It isn't like the nitrogen gases or molecules are warm and the water vapor molecules are cold. They're all the same temperature. To have the same temperature, to have the same internal energy, they all have to have the same kinetic energy, which means the light ones have to really be moving fast, and the heavy ones don't really need to be moving so much. I like to picture it like a crazy traffic scene, where the traffic is all moving along, wiggling around every which way, all these vehicles, but some of them are big heavy vehicles like cars and trucks, and some are light little vehicles like bikes. And in order to all have, the same about kinetic energy, the bikes have to move a whole lot faster than the cars do, because they're just not that heavy. They have to move fast to have as much kinetic energy as like the cars do. And in the same way, in the atmosphere, a good example of a system where many gases are mixed together, the light gases have to really be moving very, very fast. Their little molecules are really wiggling around compared to the heavier molecules of things like carbon dioxide and nitrogen and so on. Why we have to spend some time understanding this is because this is going to connect us to this idea of temperature and eventually absolute temperature scales. But for now, we first have to get through how we're going to describe temperature. Well, you know about the units of temperature in terms of Fahrenheit and Celsius. You survived the first homework set. I'm going to throw in a third temperature scale here. Again, if you took like any high school science class, you've probably already seen the Kelvin temperature scale. It's named after William Thomson, the first Baron Kelvin. He was a late 19th century scientist in Scotland, and he was appointed to the House of Lords, hence the Baron Kelvin part. And just another old dead white guy of science, but I mean, obviously one of the greats. He's credited with just figuring out the lower temperatures of the value of absolute zero and things like that. If we connect our ideas of how temperature is about the kinetic energy of the molecules, we can kind of see how the Kelvin temperature scale works. Because absolute zero, 0 Kelvin, will be the temperature at which the molecules are moving so slow they're not moving at all anymore. They don't have any kinetic energy. You can't get colder than absolute zero because you can't get slower than not moving at all. If the molecules were absolutely not moving at all, you'd have a temperature of absolute zero, or 0 Kelvin. You'll notice I'm saying 0 Kelvin, not 0 degrees Kelvin. Your book does actually, for some reason, use the term degrees Kelvin, which is uncultured? I don't know exactly the right choice of word. The correct term is to not put the words degree when it's Kelvin. Degrees Fahrenheit, degrees Celsius, Kelvin. But it is true that nobody's gonna fail the class because they said degrees Kelvin or something like that. But strictly speaking, Kelvin is an absolute scale. It doesn't have degrees. It is a fairly simple conversion from Celsius. The temperature in Celsius plus 273.15, a number that was discovered by Kelvin, gives you kelvins. So like if the current temperature is 32 degrees Fahrenheit, that's 0 degrees Celsius, 0 plus 273.15 is 273.15 Kelvin. The freezing point of water is 273.15 Kelvin. Absolute zero is 0 Kelvin. So 0 on the left-hand side would mean that C is equal to negative 273.15. Negative 273.15 is the coldest temperature possible. It is absolute zero. Just to kind of give you a little perspective then on that, average temperature of the Earth works out to about 288 Kelvin. We'll see other examples here along the way, but the book is, I guess I'd say, not worrying so much about the students as I would like to see. They're going to be a little bit inconsistent in this book. The author is going to use Kelvin, K, in calculations. When we have to do an equation, he's going to tend to put Kelvin in there. He'll always tell you what units it needs to be, but it's going to be Kelvin. On the other hand, when the author is showing you a map of temperatures or a profile of the temperatures in the atmosphere, the author's going to use Celsius for that. I wish that they had just picked one and stuck with it, but that isn't how it worked. Okay, but don't worry. It's always going to be explained and so on as we go along. Before we go on to the second part of this lecture, I'd like to ask a couple quick questions just to make sure we're all on the same page. Question 1. If you have a 60-watt bulb, 60 watts refers to the blank that the bulb uses. It's energy, it's power, or it's temperature. Alright, pick one of those 3 choices and follow the link below this video to get some feedback before you move on to question 2.